Okay, welcome back to part 3 of this Bohr model series that we've got going on here. So we'll be talking about different ways of representing these energy shells. How do we calculate the energy? Sorry. How do we calculate the energy required to get me from one shell to another? And how much energy is released as you drop down from one shell to another? And let's just talk about certain things like these diagrams here. So these are energy diagrams. Now the cool thing about energy diagrams is the scale on the side here. You can see the scale on the side. Down at the very bottom, that's our ground state. As I get closer and closer to the top, up to the very top, you don't see it, but this would be n infinity. Right now it's n6 is the top here. But n infinity would be our ionization state. And you get those lines start getting closer and closer and closer and closer and closer together until we're at that n infinity. So we call that the ionization state, or n infinity. Now, the numbers on the side of this one, so this is the typical way we usually see our energy diagrams, with these negative numbers on the side. These negative numbers are the energy equivalents in electron volts, right? You can see the scale on the side. These are the energy equivalents that you would need to ionize this atom. If I have anything more than 13.6 electron volts, I would get to zero. Zero would be up here somewhere. You don't see it. On most pictures, you don't see it. But if I would get to zero energy, and I would be ionized. So anything more than this, I would ionize it. So gamma electron, or gamma high energy X-rays and ultraviolet could ionize this. This is for a hydrogen atom here. At that level, if I was at this state, so electron was sitting there about to go down, but say it got hit by something else while I was here, I'd only need 3.4 to be ionized. And if I was at this one, I'd only need 1.4 electron volts to be ionized. So it gets less and less as you go up. Okay? In this diagram up here, you can see they use positive numbers. That's fine. But if I'm going to use positive numbers, I would put the ionization state there to represent, if I get to this point, that's how much energy is required. If I was at the very bottom from the zero to be ionized, you can see it says ionization here, ionization state. The ground state is always the first one. This is stat, but should say state. Right, so the ground state, I'll write a little E in there just for the fun of it. Right, so my ground state's down there. I don't like the positive number way of doing this thing, but that's fine. You can use positive numbers sometimes too. Sometimes it's nice and easy to see, oh, if I will go from zero to the first state, that's 10.2. Right, if I go from this state to this state, I can see that's like 9 point something to get from this one here. If I go a little bit more, that's only like 0.7. From this state to this state, you can see it's a little bit larger. Okay? They don't show all the energy states in here either. There should be more energy states. So when you go up to 4, there should be 5 and 6, maybe 7 and 8 in there as well. Okay? So most of the time you see this kind of diagram, the nice flat diagram, but it kind of represents this circular diagram where in the middle you have the nucleus, the ground state's the line on the very bottom, n is equal to 1. Okay? Now, all these series, you can see the Paschen series, the Balmer series, and the Lyman series on both these diagrams here, because they do represent hydrogen atoms, are just the series of light spectrum that were discovered by that person. So Balmer, the first one, the Balmer series, was discovered first because, visible. So I can see those ones. We can separate them in a prism. We can look at them without any, just with the naked eye, and we can see that series. So the Balmer series was discovered. That was all the transitions down to state 2. As soon as you go down to state 1, because of this jump here from state 1 to state 2, because that jump is so large, all of these lines here that are going down to state 1 are going to be ultraviolet, right? Because that energy difference is much bigger. And then you can see here for the Paschen series over here, these states are smaller than the red one here. That jump down is smaller than this red line. So this is infrared line. These are all infrared, and then you get smaller as you go over here. You can see a bunch of smaller ones here. Okay, so those are just the different transitions. Now, their transitions down, that would be released. But if they were transitioned up, it would be absorbed. It would have to be absorbed the exact same that it would release in terms of light. Okay? So I can create an absorption spectrum or a bright line spectrum from these lines as well. Yeah, so we use energy diagrams because of the scale, how things get smaller and smaller and smaller. If I were to use a radius diagram, which we never do, it would require, if I were trying to scale, the lines would get larger and larger and larger outwards at a square rate. So one distance would be, is it squared? I can't remember exactly what it is. Maybe I think it's like squared, like 4 squared, 3 squared, 9 squared, 1 squared. So they're getting bigger and bigger and bigger as you go out. And the diagram just gets a little bit unwieldy. The energy the other way around is the inverse square rate. So it just gets smaller and smaller as you go further out. So it's easier to draw an energy diagram versus a radius diagram. Okay. So how do we use these diagrams to do anything? Well, if I want to calculate the wavelength of light that when an electron drops from the third to the first energy levels, from the third to the ground state, you just use the numbers on the side. So the third state is 1.5. So the energy on the third state is negative 1.5 electron volts. The energy on the first state is negative 13.6 electron volts. So the energy that's released by the photon, or released by the electron, in the form, it's always released in the form of a photon as well. In one photon too. If I jump down from one level to another, I get one photon. But I could jump down multiple levels as I go. So if I'm at level 6, I could go down to level 3, release an infrared, go down to level 2, release a red, and then go down all the way to 1, release an ultraviolet. Or I could just go from 6 all the way down. But every jump is just one photon. So to find the energy released, I should stop talking and go home. I would just find the difference between the two levels. So the difference between the two levels, if you go the wrong way in the subtraction, just get rid of the negative, right? It's always going to be a positive number anyway. So I would go negative 1.5 electron volts minus, and if you want to, you just get rid of the negative numbers too. You just try to find the difference between the numbers. So minus the negative 13.6. That's the weird way to draw that 3 electron volts. So the energy released would just be the difference between the two levels. So I'm going to pull out my electron here, or pull up my calculator. 13.6 minus 1.5. I get 12.1 electron volts. If it's negative, just get rid of the negative sign. Just write down the positives. And the way I typed in my calculator, I just used positives anyway. I went 13.6 minus 1.5. I'm just trying to find the difference between them. So the energy released from the third to the first is 12.1 electron volts. Now, how is it going to help us find the wavelength? Well, we're going to have to go back to Planck's formula that says, well, actually it says HF, but we can use HC over lambda to help us on this one. So lambda, our wavelength, is equal to HC over the energy. And because I'm in electron volts, I'm going to use the 1.41 times 10 to the negative 15 electron volts seconds times the speed of light. Divide by my energy, 12.1 electron volts. Okay. 4.14 e to the negative 15. So I get 1.03 times 10 to the negative 7 meters. I'm going to put that into nanometers. That's 103 nanometers. So I know that's not visible light. It's on the shorter side, because remember, visible light stops around 300, 400 nanometers. Let's say 400 nanometers. If that's the case, this is definitely in the ultraviolet range. There you go. Let me write that out. Most likely UV light. That's a V. That's a U. Okay, cool. Now, what's the energy of a photon of light required to cause an electron to go from the third to the sixth energy level? So I'm going to back up here. So I want to go from the third to the sixth. That's in that Passion series there, so it's probably going to be infrared. What's the energy required? And then maybe at the same time, I'll just do the wavelength as well. Why not? So what are we at? The third is 1.5, and the sixth is 0.38. So the sixth is negative 0.38, and the third is 1.5. These are all negative numbers. Okay. Okay, so to find the energy required, again, you just find the difference. So I'm going to go negative 0.38 minus negative 1.5. Like I said, you don't have to put the negatives there, but you just have to find the difference between the two numbers. Okay, so I just want to go up here and just double check and put the right numbers. 1.5, that's the third. 0.38, that's the sixth. Yeah. Let's go back down here. So the energy released in this situation, absorbed, that would be required, is 1.12 electron volts. That would be exact. You need that exact amount of energy to get from that level to that level. Okay. If it was just a little bit more, it wouldn't work. If it was a little bit less, it wouldn't work. It might get me to the next level, or the level below it, or maybe not. If you wanted, you could find the wavelength to this, but it just specifically just found the energy. I want to determine the energy of the photon. Cool. So that's also the same amount of energy an electron would need to do the same thing. Remember, electrons don't have to have the precise energy. So it could have a little bit more. The electron will just give up what it needs and then take the rest off as kinetic energy. Determine the energy of a photon of light required to cause an electron to jump from the third to the sixth. Is that just the same question? That's just the same question. I'm just going to skip that question. Okay. We could change the question and make it a little bit more exciting. Yeah. Well, really, there's really not much else you could do. It's just finding the differences between the levels to find the energy required to go up or down. I don't know if I have other questions in here. Yeah, it kind of just stops here. I wanted to make the last video for this series. But if I can cross this one off and say, just one second. Okay, so I added a few questions here. I got rid of this one here on this page because it's the exact same question as this one. But I added 2 new questions here, because these are very interesting questions because they bring up the points that I brought up in the previous video about electrons and photons and how they behave differently when they collide with electrons and atoms. So first question is, what energy level will an electron in ground state be excited to if struck by a 12.5 electron volt photon? The next question is the same question, essentially. What energy level would an electron in ground state be excited to if struck by an electron with 12.5 electron volts of kinetic energy? So the first one is the electron in the atom gets struck by a photon. The other one is the electron in the atom is being struck by another electron. Okay? And they do behave differently. So they're not going to be the same answer. And I purposely made it so it's not the same answer. So let's go back up here. So if I'm in the ground state right now, I'm at negative 13.6. So 12.5 is not going to ionize me. Ionize me would be anything more than 13.6, or exactly 13.6. So if this was these are both 13.6, the atom would be ionized. 12.5 probably will get me somewhere. Let's see. So I'm going to start 13.6. So the ground state of the first state here, it's at negative 13.6 electron volts. Okay, so what I'm going to do is I'm going to add the 12.5 electron volts to this number. I want to figure out where I could land on my scale here. So negative 13.6 plus the 12.5 that we have. And I'm going to land at negative 1.01 electron volts. It's going to be the same for both these. So I'm just going to put the same math down here. I'm going to shortcut this later. Okay. So I'm going to add that. So where does this land? Which level is negative 1.1? So let's go back up here to my graph here, and try to find negative 1.1. So negative 1.1 lands somewhere between these two right here. So this is negative 1.1. You have to just watch out for the scale here. Okay, so it lands somewhere in between these two. Actually, I made it so it's almost precisely halfway between these two. So negative 1.1. Now, because it's halfway between two energy levels, it's not going to be used by the electron if it's a photon. So because this is a photon in the first question, it's struck by a photon, this electron is not going to use it. The photon will just pass straight on through. Either the photon's smart or the electron's smart, I can't remember which is which. But somebody just knows that they're not going to be used, and so they're just going to pass straight on through. Not even going to be a test. They're not going to like move up and then move back down. It'll just go straight on through, and nothing will happen. So what energy level will it be excited to for this next one? It's only going to be excited to the first energy level, since the photon is not exactly the correct energy. Right? It needs to be perfect for it to get to the next level. So if I wanted to say get to energy level, let me go back here, energy level 3 from the first level. So if I want to go from 1 to 3, I think we did that here. If I wanted to get to 1 to 3, I would need 12.1 electron volts. Pretty much exactly if I was a photon to get to that one. If I wanted to go to the fourth one, I would have to have 12.75 electron volts. Because this lands in between, the photon's not going to be used. Okay? But because the next question is all about electrons. Now the electron doesn't have to be exact. It just has to give up enough to get me to a level. So because it's between levels 3 and 4, it has enough to get me to level 3. And then it just keeps the rest. All right, so the third energy state. Since that only requires, that says requires, if you're mentioning, requires 12.1 electrovolts to get to that level. So they do give us different answers. If it's not exact, it's not used at all. It's not even going to get me close. It's just going to just not be used if it's a photon. But if it's an electron, then it could just give up parts of its energy and say, okay, here, take what you need. I'll keep the rest. So it gives it just enough to get to the third, and then keeps the rest for itself. And there'll be 0.4 electron volts of kinetic energy, and off it goes. Okay, the Bohr model can be used to help us explain a bunch of things, specifically the spectra that this whole math part up here is all about. It also explains how the periodic table, why is it ordered the way it is because it's all about these valence electrons and how there could be a max of 2 electrons in the outermost shell or 8 in the next 2 shells, etc. There's a repetition in the electrons in those. So the Bohr model helps us explain that. We're not too concerned. I won't be asking questions about that anyway. It explains the spectrums. It explains all the other spectrums too. They're just a lot more complex, right? What else is? It does have a weakness in that it's not super precise about it, but it does help us explain other spectrums. But it also doesn't get away with the fact that those electrons are technically orbiting. So they should still be emitting electrons or energy, sorry. And if it should be emitting energy, they should be collapsing on itself. But Bohr just says, whatever with that, it's garbage, right? As long as you're in the right shell, it doesn't do it, right? That's its weakness. Like, you can't really just say that to most of the time, like, oh, just floats, plane just floats because that's just because when they're in the air, they just don't obey the laws of physics. That's why planes fly. Right? No, you can't say that. You can't do that. Right? So they had to fix that a little bit. So we come back to de Broglie. De Broglie just talks about how these electrons, they're now behaving as if they're waves. And for a wave to exist in a specific shell, it just has to be constructively interfering. So by the time it wraps back around, it just wraps back around on itself. It becomes what we call a standing wave. And if the waves don't line up perfectly, they just kind of cancel each other out. And I'll have some links in the doobly-doo there for you to, or in the classroom, sorry, I keep on saying doobly-doo, for you to watch about this and how the waves can explain the fact that electrons can only exist in certain shells as well. Well, again, we're not too concerned about this. De Broglie, you just have to know that de Broglie fixes some of the problems of Bohr. We're not worried about any math in that case. And that's it. That is the history of all the atoms. That's the end of this week. Next week, we're going to be talking about isotopes, mass defects, radioactive decay. The next week after that, fusion and fission. The next week after that, which is the end, some optional videos about the Standard Model and subatomic particles, quarks, and stuff like that. Hopefully, that gives us that's 3 weeks there. Getting near the end. So I'll see you then. Bye.